So for our first example, what we're going to do is find the terms up to n equals 4 of the Maclaurin series for the function f of x equals square root of x plus 1. That's the function that I put in the introductory example. I showed that as on a graph. We're going to use that function. So even though the Maclaurin series itself goes on forever, it's got ascending powers up to the infinitieth power of x. We're just going to find the first four terms, and we'll learn a little bit later that there's a special name for that, which is the Maclaurin polynomial. But I'm getting ahead of myself. So in order to do this, I've put the formula for m of x right here. So let's expand this. What we're going to need is the first four terms, or the terms up to n equals 4. There are actually going to be 5 of them because we're starting with n equals 0. That's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed plus f fourth derivative. We don't write 4 prime symbols. After when we get up to the fourth derivative, we start writing it in this special notation. So that's f with the superscript parentheses 4. That's going to be 4 factorial x to the fourth. So this is going to be the terms up to n equals 4. So let's just look at what we need in order to be able to do this. We're going to need, first of all, we're going to need the first 4 derivatives of f. We're going to need to evaluate them all and the original function at 0, at x equals 0, and that's it. Once we have that, we'll be able to write out the series. So that's really all you need, is you need some derivatives, and you need to evaluate them at the center. So if f of x, let me do this in purple, it comes out a little better. If f of x equals x plus 1 to the 1 half, then that means that f prime of x equals 1 half x plus 1 to the negative 1 half. F double prime of x equals negative 1 fourth x plus 1 to the negative 3 halves. I am using the chain rule, but since the derivative of x plus 1 is just 1, you don't really see the chain rule step. So f triple prime of x, I'm continuing to use the power rule and the chain rule together, so that's going to be 3/8 x plus 1 to the negative 5 halves. And finally, the fourth derivative at x is, this is negative, so negative 5 times 3 is negative 15, and 8 times 2 is 16, so that's negative 15 over 16, x plus 1 to the negative 7 halves. So I now have the first 4 derivatives. I have f and its first 4 derivatives, which is exactly what I'm going to need to write out this series. So let's evaluate them at 0, because it's not enough to have these expressions. You see that I actually need to evaluate all of them at 0 to put them right into the series. So this is going to be, let's see, f of 0. 0 plus 1 to the 1 half is 1. F prime of 0 is going to be 1 half times 0 plus 1 to the negative 1 half, so that's just 1 half. F double prime of 0 is negative 1 fourth times 0 plus 1 to the negative 3 halves, which is negative 1 fourth. As you can see, we've chosen this fairly carefully so that all of these x plus 1, to the any power, once I make that 0 plus 1, I'm just raising 1 to various powers, and that's always going to be 1. So these all come out to their coefficient. So that's f triple prime of 0 is going to be 3/8 times 1 to the negative 5 halves, so that's 3/8. And the fourth derivative at 0 is negative 15/16 when I plug in 0. So I now have all the derivatives that I need. Now I'm ready to write out the first 4 terms of the series. So that's going to be m of x is equal to f of 0, which is 1, plus I have 1 half times x, and then I have negative 1 fourth over 2 factorial is going to be, that's going to be negative 1 fourth over 2 factorial. And you can write it this way. It's not necessary to simplify these numbers. This way I can actually see, if you write it this way, I can actually see that you understand what the pattern is. So that's negative 1 fourth over 2 factorial times x squared. And this is going to be, let's see, plus the third derivative is 3/8 over 3 factorial x cubed and then minus 15 over 16 over 4 factorial, because this is a negative 15/16, so I'm just subtracting that, x to the fourth. And in fact, I can go back and fix this one. So that's going to be minus, instead of plus negative 1/4, I'm just making that minus 1/4 over 2 factorial. So this is the first four terms. This is the first four terms of the Maclaurin series for that function, f of x equals x plus 1. What is it giving us? Well, it's giving us a quartic function. A quartic is a fourth degree function. It's giving us a quartic function that's centered at 0 and that probably very accurately traces this curve at x equals 0. So let's see. This actually has, yeah, you can kind of see what it looks like. It's going to be, it's going to look sort of like this. So you see, as I go far away from the center, as I go very far away from the center of x equals 0, this function may not look very much like the function, but look at how closely it's going to trace the function right near x equals 0. So much better than, let's say, the line does. So that's what this is all about, is we're creating this fourth degree function that looks, that's at least going, as long as we're near the center, at least is going to look very much like the function. Just focus on what it looks like, let's say, in this range. We can see that at least in between these two red lines, it traces the purple function very, very closely. Now what I want to do is make the case to you that this formula has some meaning and that it works and that it gives a good approximation. So let me show you why that is the case. Let's take this function, m of x, and differentiate it and evaluate its derivatives at 0. So what we're going to do is we're going to differentiate m of x and evaluate mn of 0 for n equals 0, 1, up to 4. So we're going to see how m compares with f in this very specific way. We're going to, we want to see is if it matches f and its first four derivatives when we evaluate them all at 0. You see what I mean in a minute. So let's take m of x. We already know what m of x is. Let's that's not going to get the whole thing. There we go. Okay, so there's m of x. I'm going to take this box away. Let's find the derivative of m of x. In fact, let's find the first four derivatives. The first derivative, I'm going to do this term by term. So this is going to be, the derivative of 1 is just 0. The derivative of 1/2 x is 1/2. And then this is going to be 2 times 1/4 over 2 factorial. So 2 factorial is actually just 2. So that means that when I multiply 2 times 1 over 2, I get, they cancel out, and I just get 1/4 x. Now, let's find this derivative. So this is going to be 3 times 3/8 over 3 factorial. Let's write 3 times 3/8 over 3 times 2 times 1 x squared. We're going to simplify that in a minute. And then this is going to be minus 15 over 16, or rather I need the 4. 4 times 15 over 16 over 4 times 3 times 2 times 1 x cubed. Okay, so let's see what simplifications I can do here. I have 3 times 1 over 3. Those are going to cancel each other out. So I can simply, these disappear, and I just have 2 times 1, which is 2. So that's going to be over 2. And here, this 4 and this 4 and this 4 are also going to cancel each other out. So what I have here is going to be, let me erase these. Those cancel, giving me 3 times 2 under there. I don't have to write 3 times 2 times 1 because that's just 1. So here's m prime. What I'm going to do now is I'm going to zip through the algebra to do the next 4 derivatives. Sorry, not the next 4 derivatives, the next 3. I'm going to do the second, third, and fourth derivatives. Okay. So I now have have m in its first 4 derivatives. Now, let's recall what let's recall what the first f in its first 4 derivatives evaluated at 0 were. So f in its first 4 derivatives, put them out here. That's f in its first 4 derivatives evaluated at 0. Let's evaluate m in its first 4 derivatives at 0. For m of 0, look what happens. I plug in 0, I get 1 plus 1/2 times 0, plus this coefficient times 0 squared, plus this times 0 cubed, etc. In other words, because I'm evaluating this at 0, all of these terms drop out. The only thing I'm left with is the first term, so m0 is equal to 1. M prime of 0, I get the same thing. I get 1/2 minus a bunch of things that are all multiplied by 0, so this is just going to equal 1/2. M double prime at 0, I get negative 1/4 plus a bunch of things that are going to be 0. So negative 1/4 m triple prime of 0, I get 3/8 minus 15/16 times 0, which is just going to be 3/8. And m fourth derivative at 0 is just going to be that constant, negative 15/16. Now take a look. Compare m and f at 0. The values are all exactly the same. So what is it that we're really doing when we construct the Maclaurin series? This is how it works, is that if I keep taking the derivatives, I get the same. I get the same value at the center. Let's go back to this drawing. If I were to use the tangent line at 0, there are two things that it agrees in. Its value, in other words, the value of the function is the same at 0, is the same as the tangent line at 0. That's why it's tangent, because they intersect at that point. And the slope of the function is the same as the slope of the tangent line. So what happens when I say that? So this is what it means to say that the 0th derivative agrees at 0, and the first derivative also agrees at 0. The 0th derivative gives the actual value of the function. The first derivative gives its slope. The tangent line and the function have the same value and the same slope at 0. That's what the linearization has in common with the original function. When I go on and construct a Maclaurin series or a Taylor series where I keep adding more and more powers, what I'm saying is that even higher derivatives agree. So what this means is that in addition to the slope agreeing and the value, when I say the second derivative agrees, remember what the second derivative represents. You learned this in the optimization unit in Calc 1. It represents concavity. So I'm going to go back here and try to draw this to explain what that means. Let's suppose that I have a function that looks like this. We said that this function had up concavity, meaning that its second derivative was greater than 0. What we never told you in the optimization unit, because we only used concavity to talk about whether it was positive or negative, is these two functions both have upward concavity. Let me draw this one in a different color, actually. Both of these functions have upward concavity, but I would say that this has an f prime prime of, let's say, 1, whereas the purple one has an f prime prime of 10. They're both greater than 0, but concavity is still a thing we can measure. It measures kind of the sharpness of the curve. So that when we say that two functions agree, here's the function that we're approximating again. And when I say that it agrees that when I say that the approximating function, let's say an approximating parabola, let's say I only went up to degree 2, when I say that it agrees with the function up to up to its second derivative, what I'm saying is it has the same value, it has the same slope, and it also has the same curviness, the same concavity. Would it surprise you to learn that there are geometric interpretations of the third derivative, the fourth derivative, the fifth derivative, etc.? There are actually names for them. So if the second derivative is concavity, the third derivative is called kurtosis, or also called, believe it or not, jerk. It has to do with the idea that if we're interpreting this as acceleration, if we say the second derivative is like the acceleration of a moving body, the third derivative is the rate at which the acceleration is changing. So, a constant acceleration, like when you're in free fall under gravity, it feels like you're accelerating, but the rate at which you're accelerating doesn't change. If you're in a car and you're accelerating and then suddenly you slam on the gas pedal, then you feel the car jerk ahead. That's a positive third derivative in that case. The names for the fourth derivative, the fifth derivative, and the sixth derivative are called snap, crackle, and pop. They're sort of whimsically titled. I know that some of you are not in the United States. There's a cereal called Rice Krispies, and the mascots for it are three really small guys named Snap, Crackle, and Pop. So this has nothing really to do with what the function looks like. We don't say that it's more crackly in some way. It's just these are just the names for it. But the point is that if I have, let's say, if I've constructed the Maclaurin series up to degree 6, what I've done is I've created another function. It's not the original function, but it's a function that at the center point has the same value, slope, concavity, kurtosis, snap, crackle, and pop as the original function. That's pretty similar. That's why this curve that we're able to create is a very good approximation of the original curve, because we're ensuring that all of these derivatives are going to be the same as the original function as long as we are at the center. It's not true anyplace else, but it is true at the center. So that is what Maclaurin series is all about. For the rest of this topic, we're going to be constructing the Maclaurin series and also determining just how close we actually get to the original function when we stop the series and just use a polynomial up to some degree.